Okay, welcome to Strength of Material. Today is September 27. I'd like to share my screen. Okay, last week we went through stress-strain relations, which relate strain and stress at a point where we define a component, stress again strain component, and very importantly, 1D version of this relation is that simply strain equal 1 over sigma. That is a 1D version, and 2D version is the we have a 3 components, sigma xx, sigma yy, and sigma xy. Okay, I would like to close my window. Okay. And we have, that is a 2D version. Now this is a 3D versions. We have a 6 component of strain and 6 component of stress. And notice that we have a Young's modulus here, and here, and here, and Poisson's ratios here, and shear modulus is here, and this apply to a 3D body. Now, this is the body under stress, and there will be a strain, but stress is a purely mechanical stress. Now, let's say we have a body is subject to a temperature, say delta T. Back to the slide, where here we have not only, let's delete these terms. We just focus on 3D, and 2D and 1D version can be easily obtained from this 6x6 equation. But anyhow, in addition to this mechanical stress, let's say we apply certain temperature together, then this body will certainly expand depending on the temperature. And this strain, due to a temperature, we will have additional terms, which is now we call a thermal strain, which is the alpha, and there is a no shear. So this is a term proportional to a delta T apply. So 1D version of this relation is that epsilon equal 1 over E sigma and plus alpha delta T. So let's say we have this just 1 bar and apply subject to a sigma on the right-hand side, on the left-hand side, and then at the same time, the delta T is applied. Now, what will happen to this body? Well, since one-dimensional, we consider only axial extension. So there will be a certain amount of the strain, which is a proportional to a sigma, which is called mechanical strain. And also, there will be another strain. So 2 terms, one is due to a sigma and the other one due to a delta T. So alpha delta T. So this is a total strain, which we observed. Okay, that is important, which we observe. So this total strain again consists of stress term due to a stress and term due to a delta T. And this concept is expanded to a 3D and very similar, except that there is no angle change in due to this temperature. In other words, say we have a 1D body and delta T, there won't be like shear strain, there will be no such a strain, okay? So there always a zero shear strain. Okay, so summary, we have actually this is what I explained. This is only delta T, and all the stress, let's say all zero, and only delta T, then there will be a strain, extraction and strain in Y direction and strain in Z direction, all proportional to delta T, and proportional coefficient is the same, which is called a coefficient of thermal expansion. And see, this is the 1D, one-dimensional version, and this is the 3D versions. And if we try to plot these 3D versions, well, it's simply, this is original before delta T, then it will expand. It will expand in every directions like that. Right? So each direction, X direction, Y direction, and even Z direction, we have a strain alpha delta T. So alpha is the important value, and alpha is the one regarding the CTE coefficient of thermal expansion. Okay, expansion. So in short, we call CTE, very famous material property. So for each materials, we have Young's modulus and Poisson's ratio, and shear modulus is always calculated from this E and mu. So G shear modulus is always 1 plus mu. Now there's another independent material property, which is called coefficient of thermal expansion, and CTE. Okay, so that is the what I'd like to mention today, and now I'd like to spend about some time to describe of this chapter 7 failure criterion. Okay, failure criterion and stress strain, stress concentration, and fatigue and creep. We're not going to cover too much about this advanced topic, but mainly failure criterion. But what is a failure criterion? What is a failure criterion? And that is the important concept. And this is another material property. See, we, as a material property, we have a stiffness and strength. Now, as you know, once we calculate the stress, as we emphasize many times, once we have this stress and the should be less than strength. Otherwise, the material will fail or break. So that's why we need to compare with the strengths whether the material will not fail or not. So that is the 1D version. Let's say we have 1D version means that let's say we have only sigma xx, and which was calculated from equilibrium and stress-strain relations and geometry compatibility. Now, once we have a sigma, we as a designer, we have to confirm that this stress sigma should be length less than a certain level of strength, which is a material property. Sigma yield is a strength. So whatever stress we calculate from equilibrium, stress-strain relations, and geometry compatibility, this stress should be less than this strength. Sometimes this is yield ultimate, completely break ultimate strength, but as a designer, this stress should be less than yield strength. Okay, this is YIELD, yield strength. So this is an important failure criterion in one-dimensional case. Now, the main point of this a failure criterion is that three-dimensional case. Three-dimensional case means that, let's say we have a three-dimensional stresses, not just 1D. 1D means this level, but let's say we have a 3D stresses, all 6 components. The question is that will the material fail or not? That's the questions we need to answer to. There are several theories. Okay, this is a theory. Very famous theory is the Biomechanics yield criterion, and second is the Tresca yield criterion. Biomechanics is sometimes called maximum distortion energy theory, and Tresca is called maximum shear stress criterion. I'm not going to go in detail why those theories are called like that. But I'd like to emphasize how we use this failure criterion. Okay, again, as I mentioned, we want to apply this failure or yield criterion in three-dimensional cases. Three-dimensional cases, first we have sigma x and sigma y and sigma z and sigma xy and sigma yz and sigma zx, all as a 6 components like that. Okay, 6 components stresses. Now the second step is that we calculate principal stress, sigma 1 and sigma 2 and sigma 3. Oh, what is a principal stresses? Well, principal stresses is that the stress which will have a maximum tensile stress in a certain direction. In other words, let's say we have a x, y, z. We have this 6 component of stress. But at the same point, if we change certain directions, let's call x1 and x2 and x3, and here shear stresses all disappear, only normal stress exists. That they are called principal stresses, and in 2D version we call a Mohr circle. Mohr circle is the one related to this how to calculate this principal stress. So we need to study from 1 to 2. I will cover some other time, but let's say we have 3 components and normal stresses, and 2D version, we have only sigma 1 and sigma 2. And again, 2D version, we have a sigma XX and YY and sigma XY. And 2D version, we say we have a sigma 1 and sigma 2. Okay, and this axis and that axis has a certain angle. This is the certain angle. And now how to calculate it? That is the one related to, the procedure is called stress transformation, and the simple way is using the Mohr circle. But let's skip that one. Let's just start with 2 normal stress components, and how can we say that this material will safe or not? See, now we have a 2 stress. That is the big point. The material property we only have is the sigma yield strength, and now we have a 2 components. Now this von Mises theory says, okay, this is the A function. This function comes from all the derivations, and it says this function remains a constant value, and this will reach certain value when fail. Okay, so let's say this is a 1D version. 1D version means that F sigma 2 and sigma 3 are 0. Only sigma 1 is the sigma yield. So if we put 0, 0, 0, 0, only sigma 1 and, is a sigma y and sigma. So two y's of a sigma yield scale, right? And which means that this constant value was unknown. Again, whenever material fails, it reaches certain value, which is a constant, regardless of 1D version, 2D version, and 3D version. That's what the von Mises theory. So this constant value was determined from a 1D because we already have this yield strength from a stress strain curve. So now this is determined as twice of sigma yield scale. And then put it back to here, okay, put it back here. And von Mises theory, now you can see that. This is a von Mises theory. This function on the left-hand side should be less than twice of sigma yield scale, okay? So this is all the stresses, sigma 1, sigma 2, and sigma 3, which you will calculate from the equilibrium and stress and stress and strain. There is the relations and geometric compatibility, and these should be a sigma yield. Okay. Again, I'm trying to say that these stresses, the terms from a 3A+1 flow chart. In 2-dimensional case, well, simply we put the 0. That's all. If 1-dimensional case, well, we put the 0, and left and right, you can see easily there's an equal sign there. So again, there could be different explanation, but this, as far as I understand, this version is the most simple, simplistic version of understanding von Mises. Okay. There is another theory, as I mentioned, Tresca, but Tresca, I will skip that one. I will re-explain again whenever needed. Okay, but I like to emphasize what's the concept of this failure criterion. Failure criterion. Again, the point is that when we have a three component of stress, okay, three component of stress, how do we know whether the material fail or not? Okay, that's the question we want to answer using this failure criterion. So the conclusion is that simply we use these equations and then put it here. And if this is the equal sign, I mean less than this value, then safe. If this is equal or this is greater than 2y over strength, then its material will fail. So we don't want to design and this stress will exceed material property. Okay, that's the concept we need to understand. Okay, that's basically the theory I'd like to cover today. And now I'd like to there is some other things we need to go through. As I mentioned, we are now in the process of reviewing all the strength of material 1 and in the chapter 8, shaft and torsion, and chapter 10, beam theory. This is the most important one. I will go through these two chapters next time. Okay. Next week we have a very long weekend, but after that long weekend, I mean the long holiday, we will go through this torsion and beam, and then as we announced, we will concentrate on chapter 9, 12, 13, and 14. Okay. Now today I would like to spend time on the homework we assign or this group task 2. Okay, so I hope we have enough time to discuss about this assignment. Not assignment, I would like to call task. Assignment sounds like too much pushy, but task is for you work together as a team. I don't want to give you an answer, but I just want to clarify what the problem is. And again, we have a three material A and B and another A. So these two materials are same, and material B is the second material, but we have 3 layers. And material A, Young's modulus, okay, this is the Young's modulus, and this is the Poisson's ratio, and we have a EA and mu A, and material B has the EB and mu B. So these are material properties. And now we apply the force on the right-hand side, and this is the a rigid body, and then we apply the force F on the rigid body, and rigid body apply to force to these 3-layer structures, and this is the X and Y coordinate. Now, if we look at this way, then coordinate will be so this is the X and Y and Z. And Y and Z, as you can see that on all the edges, surface are enclosed by certain roller. This roller is this roller. So this one will certainly and pay attention to this system, and this will shrink at the same amount, right? This will shrink at the same amount, but it does not expand or does not contract because of this roller system. So if we draw this as a 3D figures, this will have certainly so always we should be able to visualize, which will help us to understand and solve the problem. So this is the a rigid body, right? A rigid body, and we applied all the forces here. All the forces here, and this will whole plane, whole rigid body will have a certain amount, which we can call delta x. Okay, that's the problem. Now the this is given, so external force F is given, and now find how much will the body deform. Means that by symbol, how much delta x we will have. Okay, define lengths. Okay, this is one of the key important. Define lengths or dimensions if needed. What does it mean? It means that to solve this one, as you can see, there's no dimensions are specified. Well, certainly all the solution will depend on the lengths and dimensions. So we need to define we have to have a certain length, let's call Lx, and let's call this one, okay, and this one, and this one. Well, we didn't say, it didn't say anything about this thickness, but we have to ask for that. That is one of the very important points. When we are given certain problem, we have to look for all the informations. And so this one, say T1, and this is a T2, and this is a T3. Okay? And another one we need to have is this. Well, this T1 to 3 or delta X is up to you. You don't have to follow. And this one is, let's say, this is basically this length, right? So let's call B. Well, some of the team already defined. This is A, B, C, and D, which is also okay. I will clarify A, B, C, D, as long as they you can have independent value, then it is okay. So define the lengths if needed. That is the very important. Again, I want to emphasize that all you guys have been studying on such a problem which already well defined. Well, but to be a mechanical engineer, you have to know how to define the problem, which means that you have to ask for the information you need to solve the problem. Okay, that's very important. And again, here I just explain for you, but from now on, you have to look for, you should know how to define and materials and forces and dimensions. Okay, and that's a very important point. And to solve that, there are one important step, that is the free body diagram. And what is a free body diagram here? Well, since the forces we apply is this F. See, there will be a certain reaction force from when you push. What will happen to this A? Well, that's the kind of a free body diagram you need to have. This, right? Sigma X and sigma X. And also sigma, I will call sigma X, the first one, you can call sigma 1, and this is a sigma 2, and another sigma x3. Okay, so this is a free body diagram, but again, also you have a reaction force applied to a rigid body, and you have a F. So to be in equilibrium, actually, you have to multiply A. You have to multiply A means these cross sections. Okay, you have a and B, D, right? So this is A, and I will call A1 and A2 and A3. So this is the force which will be discharge, and this one is discharge, and this will be the discharge. And so you can consider this is a certainly equilibrium, right? But a free body diagram, you can consider is Fx equals 0. So Fx equals 0 means you can apply here, or you can apply whole system, and these all the forces, again, this is the same as that one. So this one and F should be the same. Okay, that is the one, a force diagram, a force equilibrium. Now, another important point is that here, or this material, only this sigma x, well, there should be another one. What is that? This one, and 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 that, and that, and that, right? And all the stresses, basically each member will be a subject to, for this case, I would like to apply all tension, because we need to be consistent with the sign. So sigma x and sigma y and sigma z. So we kind of have one equations for the these equilibrium equations. Now here we can say that let's clarify. Okay, I forgot to say that. Let's, for the simplicity, material A and material A. You can say that this A, this thickness, you can call them same material. I mean same thickness. Okay, for simplicity. But if they are different, it's no problem. Or we can still solve the problem. But to understand the basic concept, let's have the same thickness, top and bottom. Okay, if some of you already start to solve the problem with a different thickness, that's fine. But that is a little bit more complicated. You can simplify the problem with the same thickness. Okay, and now you have only one equations, right? This is one equations, but there will be a geometric constraint. I don't want to go too much, but you would have a in y direction, and total y, delta y will be 0, and delta z equals 0. You understand what is a delta z? Delta z is even distraction, expansion, and expansion. There will be no delta 0. So this delta 0 and top 1, delta 0, 2, and delta 0, 3, they will be all 0, right? You should know how you calculate the delta 0, which you can calculate again, d times what? Strain z. See, this is a z, and this is a strain in z direction. And same here, d times, this is z1, and d times epsilon z2, and so on. And that is the z, and delta y, or what is a y? Y is the vertical. Vertical now is a little bit different story. Why? Because this one, it may be contract, and maybe each one can have can have a different contraction, right? So that in y direction, this total delta y equals 0, not each one. See, each one may deform, y directional deformation, but total y is only 0. So this is the procedure we need to go through. Now, I will extend this one as the September 20, this Friday. Okay, this Friday is the 29th, okay, 29. But there is another task is also has the similar to previous one, but now we have a delta t. Okay, delta t exactly same, but we have a delta t. So in the previous one, you better start with a epsilon x, epsilon y, and epsilon z, and 1 over e, and minus 1 over e, and 1 over minus 1 over e, and this sigma x, sigma y, and z. See, all they don't have any shear strength. So you don't consider shear strength, you don't consider shear stress. So only 3 by 3. I don't want to go through too much. This is the one. I just want to help each group to work together. Now for the temperature terms, if you have a temperature terms, you have a alpha and delta t. Okay, so this one you would have a certain thermal expansion, but again, even though you consider delta t this way, okay, this way delta y will be 0, and this way, say this way, and this way, and this way, we consider fx equals 0. That was equilibrium. I didn't mention, but delta x1, delta x2, and delta x3, they should be all same. Otherwise, this will like this, right? So this is the another one. And this, and that, what is that? Well, delta Z1, delta Z2, delta Z3, they are all 0. Yes, they are all 0. So again, you can see that you can define the problem and solve how much you have, how much deformation. Again, well, yeah, this is a little bit complicated, but you work together and solve. And once you get all the equation using the Excel and solve the problem. And since we, again, this one was the September 29th, this Friday, but this with the delta t, now this is October 10th. Again, next week is we have a very long holiday. So you enjoy holiday, but you have to think how to solve this problem, and you have a I'm sure you have enough time to do this. But 1 week actually is about 9 days. It's too long. So I will assign another task. This is a group task 3. So that this is the another one for you to solve and work together. Okay, this is the biomechanics problem applied to your spine. You know this spine, here, you have a spine, okay? This is biomechanical spine problem is so important for your daily life. And this is the, we call posterior, and front we call anterior. This is the medical terminology, but well, you don't have to know, just front and back, okay? You use whatever word for your convenience. And this is the spine. And this, as you can see here, this from here to there, we call cervical. Cervical, and we have a 1 piece, 2, 3, 4, 5, 6, 7. We have 7 pieces of cervical, and from here to there, okay, thoracic, this is another 12 pieces, and this is the here to there, we have 6 lumbar. So totally we have how many? Yes, 25. We have a lot of segments, and we have a 1, 2, 3, 4, 5. I'm sorry, that's we don't consider this bottom sacrum, and this is the 5. Yes, so totally should be 24. Okay, and cervical is so each one we call C 1, 2, 3, 4, 5, 6, 7, and thoracic we call T 1, 2, 3, 4, 5, and 12. And then lumbar is called L1, 2, 3, 4, 5. Okay, so this is a L, this is a T, and this is a T, C, 1, C, I would like to say, this is the 1 to 7, this is a 1 to 12, and lumbar is a 1 to 5. So totally 24 pieces. Well, spine thing is very important. So whenever you push or some push or pull, but more importantly, when you lift the weight, you look at, pay attention to what happened to your spine, and of course there is a reaction force from the ground, and certainly this has to be an equilibrium, right? This is the external force, and this is the external force. If we consider only this one and that, we don't know how much forces we apply to each spine. Well, understanding the spine, all the forces are carried by each vertebra, each one called the vertebra, a segment, and a lot of forces. Look at that. This one is the backside, okay, posterior, and this. So this is the very important role. Let's pay attention to your back. If you touch your back, try to touch your back, you can see there is a certain segment, right? Not the smooth one. It's a 1 and 2 and 3. Certain segment. I have another better another one, and now each one, let's say just a lumbar. Okay, the most typical one is this lumbar 4 and lumbar 5. Let's call L4 and L5. And this is the vertebra, and this one, this is called. I mean, this is one vertebra, and this is another vertebra, and they are connected together. This is a ligament. Ligament is a connection between each bones. Okay, each bones, and whenever we lift and push too much, and this here there will be a herniation disc. This is a disc, rubber like very soft disc, but it's too much force. Then there's disc herniations, and there's all the your nervous system go through this channel, very tiny channels from your this is your eyes and your lip and your nose, and all the nerve is from your brain, and that nerve goes inside. See, there is a gap, right? There's a small channels, and if we look at the top, and this is your nervous system. Okay, here's the nervous system, and this nervous system is kind of protected by this and that, and we have a small channels. But as I mentioned, if we have too much force, this disc, this is a disc. Okay, I will delete this one, and this is a disc, and disc is a rupture, fail. Okay, so to fail, and this disc, there is a kind of a water-like, and this is a herniation, break. And then what happened? Okay, this is actually this, and this is a break, and then it pinch the nervous system, and that's why you have a lot of pain when you have a back pain. So this is the herniation, and finally a rupture, and it pinches your nerve. So if you have a really pain here, you have a leg here, you have a hip here, hip like this, and you cannot, you feel very pain here, right? So you cannot move. And same story goes to your neck. If your neck, or you bend too much your head like that, this is a too much force, and your arm feel very pain, because it's exactly the same thing. Well, I don't want to go too much, but this is very interesting biomechanics. And now another one, this is the X-ray or MRI scan showing each, this is a lumbar. Let's say this is the your lumbar, and this is a disc, and too much force. And you can see that this one is squeezed out, and there is the nervous system. This is the nervous system. You see this yellow one? This nervous system is a pinch, and that's how you feel the pains. But this one is connected by all the ligament. Okay, all the ligament. Actually, this is a backside, and this side is a backside, and this is a backside. Okay, your back. Now, what we like to do here is that we apply what we have learned so far, all the equilibrium and so on. Mainly equilibrium in this case is that now we have a certain weight. This is very important. Your daily life, you will face this kind of problem. Let's say you have a weight. Okay, this is a W, and you have your head weight. Okay, you have a WH. Your head is very heavy, unfortunately, and this is your arm. Your arm system is also very heavy. And this one, well, this is your trunk, your say a upper body. So this is I will call WB. So this is the W, WH, W arm, and WB. Now, when you try to lift up say you want to lift from here to there, and you have to have a certainly a force equilibrium, right? There will be a certain force equilibrium, whatever reactions. But what we need to do here is that using our all mechanics topics, how much the force, okay, in the ligament. As I mentioned, we have a L5 and L4, and when you lift, there is a disc. See, this is a disc, and this is a disc, and if we have too much force, and there will be a disc will herniate and push, and there is a nervous system. Now, the problem right now we want to solve is that how much here we have a tension in this ligament. See, this tension is very important. Even though we don't have any disc herniations, this ligament can sometimes damage it. I can show you, as you can see here, this nervous system, the ligament, it can damage, and you feel really, really pain. And at the same time, this is herniations, and that's how all the pains comes from. So now this is the given. This is the task given all the W. Okay, you can define all the W and all the distance. Okay, distance means this dimension and whatever dimension you need to have. Okay, and now find and how much the forces you would have, and here say F ligament is very important, and this F ligament should be less than F star. If this exceed certain level, this will break, and there will be herniation and all kinds of pains. So say this is also given F star, and you need to find the FL in terms of all these. So FL will be given as the WI and WI and DI, and you also given this, and this should be F star. And as you can see that to lift a certain weight W, discuss, okay, really discuss between your group, discuss about how to lift a weight, what a W, whatever. Okay, so again, you can have equations, you can have Excel, you can give some values, and you can see how you can define. You can discuss about how you lift the weight. What does it mean? Well, you will see this distance is a kind of which you can vary, right? You can vary. You can, importantly, you can get the distance, you can get closer to a weight, or you can have a very far from so you have a choice that you can have a something like you lift like this, or you can have a body and bend and lift and something like that, and difference is this distance is very different, right? So discuss all kinds of issue using the result you have derived. Okay, this is the again the task 3, which also due on October 10th. Okay, please do not try to solve them just 1 day or 2 days before the due date. You have to discuss time to time, and using KakaoTalk, using the share the PowerPoint, and sometimes you may need to physically meet together, but it's up to you. Meeting together is up to you, but you have to interact. As I already explained, you installed these all the Zoom conferencing. This is the a software. I'm using this Zoom and to have a teleconferencing or to record. And you can use this one among your group to discuss. You can interactively discuss. You can see the face-to-face. You can share the screen and so on. I will certainly demonstrate someday, but you can easily try yourself. Okay, well, today this is the one I would like to cover, and please, go through what we covered today, and I will continue to discuss these topics in class and tomorrow. And one thing, as you can see, that this class, I would like you to collaborate to solve a practical problem using all the mechanics, rather than just homework or problem, predefined problem. That is the is not what we want. What you need to do is that you face the practical problem and define the problem and ask for the information and work together and collaborate to solve a real problem. Okay, that is the kind of a capability you have to build through this class. Okay, so this is the end of my class today, and I will see you tomorrow in class. And all this one again is being recorded, and you can watch anytime you like to do. Okay, so thank you.